Hello everyone, this is Min Song Lee. This is the real programming task we're going to have right now. So I don't know what's your progress for this programming assignment, but I've done the programming for this task. I've done testing this. It's work, and this is really a bad program because it's specifically only for this example. But this is fine. It's just as a start to showing you how to do things. All right, you can revise your program better and better. But before this, I'm going to run the simulation again to make things simpler. All right. The first thing I want to remove everything from the output. You can do this. Remember, I removed the output file things here by typing remove stuff. You can use this exclamation mark to repeat the previous command starting with this rm. All right. So see, this is removing this. And what else do I don't need? I don't know. I don't need a config file, right? Okay, the first thing I want to do is I want to change the field file. So I want to change the name of the species. This is the first thing I want to check to OH and O. The reason is that this will be recognized as hydrogen and oxygen, and the color will be white and red, which I don't need to tune that again. So I'm going to do this. I'm going to change the two species to O and H. And again, because it's an O and H, I need to change the interaction parameter. So O and O, H and H. All right. And after this, I'm going to run the simulation again, but this time I want to run the shorter. So I go to the control file. Instead of 20,000, I just run 2,000. All right. And then run dpd. And remember, we need a config file, right? How to do the config file, that export config and position, right? You should have this config file already. We're going to work on this one. So this is the same as the previous one. The only difference is that this is much simpler, right? This is one character name. It's easier to handle. And I'm going to copy the program I wrote here. This is a program called convert.f90, which convert the config file to another config file with the spherical assignment. All right, only for this. And let's open it up and see what is happening. Okay, so I'm going to open another terminal and just side by side to explain to you what is going on. So the master demo within the test. Yep. Oh, DPD and task. A test. All right. So here we're going to put it here. And here on the left, I'm going to open the config file. On the right is the lousy program I just wrote. And I just wrote it, and it's it's best structure a lot of locally assigned variable parameters, but that's fine. I'm going to explain to you. So at the beginning of the example, you type program mem, right? This doesn't matter, and we can do something like this. This program generate the spherical object from the config file. All right, you can always do this. Program this program, okay, or written by me is mtd at 20 April 2020. All right, implicit non and the real integer and character, and this means the length of the character. I have two character. One is called TMP for temporary. One is called ATN. I guess it's ATN. All right, but that doesn't matter. So begin of the simulation, we're going to set the number of particle, right? We have 3,000 particle here. In this simulation, we have 3,000 particle. So this is n is, you always add common after these parameters when you assign. So n is the number of particle. In the future, if you want to write into as an input, is fine. So r is the radius of the sphere. All right. So we just set it 3. It doesn't matter. You can have larger. HL is the half box size. And remember, we have 10 by 10 by 10. So the half box size is 5. And we're going to open 2 files. The first file, so let's do this. Opening the file. File handling. File handling. All right. We open the file 10, which is the original one. Config 2 is the one new configuration file. All right. And see why I have I from 1 to 5 is to read the header. See, this is line 1, 2, 3, 4, 5. 5 lines. So this is for reading headers. Header. So we don't want to change this, right? We don't want to change this for now. So whatever we read from the config file, we will write into the config2 file. So do I equals I1 to 5. We're going to read 10, which is the config file. And I check the length is 50. 50 should be long enough. So the temp is 50. For this variable, so I read this line for 50. Here, this is 48. So 50 should be long enough to cover these numbers, all right? So I read 50 and write into the config2 and undo, all right? And then we're going to calculate the distance. All right, calculate distance and decide B type. All right. So this number O is the number of the O we're going to put into the sphere. All right. So again, we're doing I from 1 to 3,000 because we're looping through looping through particles. And we're going to read the thing here, right? Actually, I don't know what is the format here. I don't know how long is the program assigned to the number. But right now, because the good thing is that I assign my added number as 1 character. So the rest will be my integer, right? So here is 19 blocks. You have 19 blocks. The 1 is for my added name. So the 18 will be mine. So the format will be like this. A1, A for character, I for integer, 18 is the length. All right. So this is actually my added name. So added name and index number. Okay. Added name and the index of the particle. This is what is. And we're also going to read the XYZ coordinate. We call it CX, CY, CZ. Coordinates, right? This is a coordinate. What's the format? You can check. This is 16 here. How many digits of digital number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the format will be three numbers of floating number with the length 16 with 10 digital number. All right, this is the format. All right, and this is for CX, CY, CZ. We're going to calculate its distance. We're going to locate this sphere in the middle of the box. Okay, So remember, this is from minus 5 to 5, from minus HL to HL. So the middle will be 0, 0, 0, right? So we just need to calculate the distance between this coordinate and the 0, 0, 0. It's very easy, right? So this is called dx. dx is the distance between in x direction from cx to 0. All right? And we're going to write, we're going to write this. All right, this is for my checking. I did a mistake when I was working on this program, so I add some checkpoint to see what is going on here. So, but you don't need to do that, just delete it. So usually we just calculate dx, dy, and dz, right? And then dr equals ds squared plus dy squared plus dz squared, right? This is the radius of, no, this is the distance between, dr is the distance. dr is the distance from atom to 0, 0, 0. All right? This is the R. Before calculating R, you need to make a PBC correction. What is the meaning of that? Let's go back to our, where is my PBC? You see these two particles, all right? If you look at these two particles, what's the distance between them? You may think, okay, the distance is this, right? This is a long distance, almost as large as the box size. But actually, it is not, because consider the periodic boundary condition. You have infinite replica around you, all right? So if the atoms are located here, on the right image, you also have the atom located here, right? So these two are the image of these two. When you are calculating the distance between these two and these two, if that is larger than the half box size, it needs to be correct, meaning that you have a closer particle in other image, which is better described for your atom and atom distance. For example, if you are calculating the x direction from here to here, which is this direction, right? You are not calculating this because you also have this one, which has a shorter than half box size. All right? So you need to, when you calculate this, you need to give the real distance as this. The way to correct that is to first check whether the distance between two particles is larger than the half box size. Remember, we have HL, these parameters. That's the reason we want to have that. And then if it's larger than half box size, we correct that by deducting the whole box size. Remember, this is the original size, and if you delete it, deduct it by the whole box, that will be like this, right? So that's these two lines for. If dx is larger than half box size, my dx equals the original one, the calculated one, with the correction minus the whole box size. If it's minus and minus less than the half box size, I need to do the plus. You can draw it on your sheet and understand what is PBC, what to correct the vector you calculate. Okay, this is the correction for periodic boundary condition. Okay, so you have dx, dy, dz, and dr. And we first assign all the atom as h, right? We just first assign this h. If the r is less than the r we assign, which is 3, we will call it O. All right, we'll call it O. Okay, and when we find this one, we assign this one, we want to increase our counter by 1. So we know how many O we put into the sphere, so the rest will be phased out and minus. After this, we're going to write the 11, which is the config2 file, our atom name and the index, and cxcyzd as the same format as the config file, and undo, and then close the file. We write to ourselves we have how many number of O, how many, and then we have how many number of H. So it's 3000. It's n minus this number. All right. So if the program is written correctly, when I compile this, that should work out. So G4chan minus O, we call it convert.exe, and the program is convert.f90. All right. And then convert.exe. Okay, we have 337 and 2663. All right, let's remember this. And then, oh, I probably will forget. 337, 2337. You know, that's embarrassing. I have a very bad short memory. Let's do it here. So we have 337, 2663. All right, two species right now. Okay. And we're going to, I'm going to leave this config file, original config 1, which is totally mixed. We're going to remove it. And we're going to copy this config 2 to config 1. All right. So when I have a config file here and I run the simulation will start with the config file. It won't generate the random configuration for you. Okay. So again, I'm running just 2000 steps and finish. And I also want to run traject VTF. And I want to copy my trajectory to desktop. And remember, we have this visualization here, right? And unfortunately, we can no longer use that because we already changed the eta name. But anyway, it's okay because we're going to, oh wait, where is it? All right, I'm going to copy that again. We're going to copy that again. So it's right here. So I already opened VND, right? So let's load the simulation and see what happened. All right, that should start with new molecule, load, trajectory, ta-da. And change the graphic. I'm going to change the graphic representation to name O, right? BDW, remember it's 0.5. I'm going to change orthographic, that curing is smaller. Right. Okay, you don't know what is happening here, right? But actually it's fine. It's already satisfied our requirement. Remember, we have a periodic boundary condition. So that is when we run the simulation, the actually particle is dissolved. But when we draw into the first one, you see, I have a particle on the 8th edge of the cubic box. That means when I do the replication for, can I do this? Yeah, I probably can do this. Trajectory, periodic. Okay. When I call out the minimal image here, see, this is the sphere. We are generating the sphere in the simulation box. And when we run the simulation, we can start with this oil drop, right? And also want to call out for hydrogen. And doing the smaller particle. See, this is what I want you to do. Now, it's hard to see, right? Because this is composed of so many B. You can change the view here. Like instead of VDW, you can do quick surface. No, this is VDW, sorry. For all you need to change to the quick surface and make a smaller radius. Is that a good idea? Yeah. See, I have so many particle. I have so many particle. It is not good idea. Okay. Okay, this is not appearing, obviously. So that's the beauty of the simulation. You always need to find the best way to present your results. Okay, but this is I want you to do to generate this. So if the program works out, you should have this, right? Okay. But that's not my point. My point is I want you to run the simulation. I want you to run the simulation. I want you to change as the final test. I want you to change the O and H parameters to stabilize the oil droplet. You know what does it mean? Remember we have that here. We are starting with the configuration, right? So now we're going to change the parameters. All right, we're going to change not 40, but say original 200. Now let's make it larger, 500, and see what happens. 500, and see whether I can stabilize the simulation. So and also we want to change back from 2,000 to 20,000. Just the regular simulation as the same simulation step as the example, right? Let's keep out. So it's the same. We're going to see how fast. Tail minus F. The upper file. So right now only 5,000. We are running 20,000. Oh, in the meanwhile, we can save our visualization state, right? So that's time that next time we don't need to do that again. Okay, this is the spherical ball. We're going to save it. Save visualization state by VIS. Okay. Voila. Control C. And then convert the trajectory. Copy it to the desktop and use VMD to visualize that. File, load visualization state. Yeah, S. Voila la. See, in the end of the simulation, my sphere is still there, right? My sphere is still there. See, as the simulation running, it is moving, right? It is moving a little bit, but it remains its position, right? It remains its shape. But that tells me the thing I don't like, right? Because I want to see the whole sphere. I want to see the oil droplet. I don't like it on the edge of the thing. I want to be the box center. You know what I can do? In the beginning, we assign the sphere as 0, 0, 0, right? But if we can add a half box in X and Y and Z, I guess that will do, right? So let's check. Let's check whether we can change our program a little bit. You know, that's the beauty of the simulation. You can always do something a little bit better. So let's close it. I want the oil drop in the center of the box. So when I'm writing this out, I assign it as the center of the box. So instead of 0, I minus a half box size. No, this is not a good idea. You know what? Let's try. I don't know. Maybe we'll fail. Maybe not. I just change one thing here. Let's do this. So half box size is 5 minus 5. All right, let's do it. So G4chan minus O convert EXE convert F90. All right. And then we do the convert. Okay, then we need to copy config2 to config and change this to number, and I run the simulation again. You know what? I don't care. Just give it a try. It takes a while, and if I fail, you can continue doing what we are supposed to doing. But here we already see we already generate the. Oh, where is this? Okay, let's do that again. I want you to at least have the image load visualization state. Okay, this is what I want you to do, to have this. We try OH equals 40 cannot hold the droplet, but OH equals to 500 will do. So my question, my text for you, which the one I'm doing right now, it's this is a text one. Text one, can you find the minimum OH parameter which hold the shape of the oil droplet? Can you do that? That must be something between 40 and 500, right? But I was wondering how large I'm going to assign to make the oil droplet not broken. Okay, text 2, which is the one I'm trying to do right now. Can you modify the program to locate the sphere, the oil droplet in the middle of the simulation box? If I fail, our class stops here. If I did it right, then I did it right. All right. Okay, simulation finished. We're going to convert it to the VTF file. We're going to copy it to the desktop, and we're going to see what is happening here. So VND. Voila la, file low visualization state. I hope I'm not embarrassing myself. Watch out. Uh-oh, still the same. All right, not working, still the same. Did I? Anyway, how do I move this? Yeah, this is at a corner. I want to move it to the center of box. Okay, this is my text for you. All right, I will still try to do that in the, you know what, I probably won't. Can you move the simulation? Can you alter the simulation to move the spherical in the center of the box? All right, that's my homework to you. Can you do it? That's so weird. By center, I already shift it to the middle of the box. Oh, I just need to change. Oh, you know what? I know what is happening, but I'll leave it to you. Okay, that class stops here, and I hope you enjoyed the lecture today. Thank you.